Hello, my name is Paul Parkinson. I wanted to talk to you today about some of the power of Oracle Database for the innovations that are happening in the industry now. And two of the biggest innovations are, of course, AI that we've all heard of and 3D that we've all heard of, and they're used together, actually. And what's amazing about the Oracle Database is the features it has had for many years now that have set it up as a perfect database engine for these data types. So one example is 3D. So in this day and age, many people have 3D printers in their home and office the same way they had 2D printers over the last decades. It's very commonplace. And this data from these 3D scanners that can be printed in 3D printers, such as basic handheld powerful scanners like this, and 3D printers generate an immense amount of very valuable information, again, taking it from the 2D to 3D space. And this information is stored in the spatial component of the Oracle database. So that's what's amazing is we can take these data types and keep them in the Oracle database and have this ability to analyze anomalies and such, but also to incorporate other aspects of the database, which is why it's often referred to as the converged database. We can, do SQL and JSON queries at this level. I mean, we can do AI processing on this spatial data, and we can really dig into the analysis of these point clouds beyond the basic, polygon, triangle, meshes that we've had in the past. So Oracle is already ready for these advancements and new influx of data coming again from examples like 3D. This data can then be, as I say, analyzed and viewed in new ways. Data that is often represented in 3D fashion, such as graphs or actual point clouds, and presented today in 2D, can be analyzed in 3D and actually viewed in immersive 3D experiences, such as with AR glasses that are available today. And so to show off some of this capability with a fairly simple example, actually, what I do is scan individuals or objects with the basic 3D scanner that grabs the point cloud and generates a mesh from it. So we have this data. We can now store this data in the database and analyze it right in the database. That's the beauty of it, is it's the logic to process the data is right in the database itself. So from there, we send it out. We can send it out to a 3D printer and print out different, obviously very specific parts or figurines and things like this. 3D printing makes that very simple to do complex things these days. And we can also visualize in augmented reality the 3D design, or simply view that on the computer. And that's what I'm doing here with this demonstration. Oracle Database 23c has a number of new and exciting features in the area of spatial, two of which are advanced operations on point clouds and the ability to generate meshes from point clouds. These features also open a number of different use cases. Here we see a hand in digital representation that has been scanned from a 3D infrared scanner. The hand file is then imported into a 3D modeling tool where a ring is added, and this hand and ring combination is in turn saved as an OBJ file. The hand with and the hand without the ring are then imported into the Oracle database. These two OBJ files have their point cloud extracted from them, and the difference between the two is detected by the Oracle database. This delta can then in turn be created into a mesh file. And this mesh file can be exported into the same OBJ file format that the original hands were in. Let's take a closer look at the use case and the overall workflow. The OBJ file that was created from the hand scan is a very popular file format first introduced by Wavefront in the 1980s and is still in use today in a number of 3D modeling tools, which is why we've chosen it for this use case. It's very common the case that such files may be stored in locations like object storage. The Oracle database is able to access all various forms of data from external sources using various APIs. The DBMS cloud package has a number of very useful operations for accessing various cloud services. In this case, we can use the create external table operation to access cloud storage where the OBJ file may be saved. This brings the OBJ file into a Oracle database table. Let's take a look at some of the operation that you might need to conduct on such files to make them appropriate for point cloud analysis. The different types for the OBJ file are presented as prefixes on each of the new lines, where V indicates vertices, VT indicates texture mappings, etc. We are only interested in the V lines for the vertices for the point cloud. And therefore here we see filtering on that information in order to create our input hand with ring and hand without ring table for point cloud analysis. Here we see the create PC unified operation. This takes a number of arguments, starting with the model, which is the PC type argument. Flat meaning that it is stored as a plain old table of dimensions rather than, for example, a block or hybrid. The source table is our input table mentioned earlier. This contains the information from our OBJ file as far as XYZ coordinates. Next, we have our base table, which is the name of a top-level point cloud object containing attributes, etc., and not the actual data, which we have brought in from the input table. The data table is the table that will be created from the information brought in from our input table, and the PCID is the point cloud identification number, which we've assigned as 1. The PC tolerance value is the value given to show how much distance between points can exist in order to consider the points as distinct coordinates. And of course, this is relative to the use case. If it's a zip code, a millimeter does not matter, but perhaps 10 feet does. The block size is only relevant for the block model, so we are using the flat model here. The SRID is an identifier for the coordinate system. Here it is random, as the hand does not have a coordinate system per se, or it is a local, as opposed to something such as an Earth-based coordinate system. Create pyramid refers to whether the point cloud should have a pyramid, in other words, multiple levels of detail, where a higher level is a summary and can be chosen from. Here we have chosen not to create pyramid optimizations. We have called the create PC unified method both for the input of the hand with the ring and the input of the hand without the ring. We now have these in the system, and we can call the new PC difference operation. This operation is fairly straightforward. We are passing in the hand with the ring, ID1, and the hand without the ring, ID2. We are putting the results, or the delta, in this file defined here, the obj_diff table. This tolerance value indicates the distance between 2 points beyond which the system should consider them different points. So in other words, if it's too small, there will be too many differences, and if it's too large, there will be too few differences. We now have a point cloud of the ring. That is the diff of a point cloud of the hand with the ring and the point cloud of the hand without the ring. We'll now proceed to convert that ring point cloud into a mesh obj file. Here we see the create tin table operation, which is a very simple convenience operation to create empty tables to store the data, so we avoid creating multiple tables, etc. manually. Create meshes is a new operation that's used to create the meshes from the point cloud diff that we just generated. So you can also use the create tin unified method, and that works on both meshes and tins on triangulated irregular networks, but we're just using the create mesh meshes operation here. So the arguments here include the base and data table that we created above, an ID, the same concept of a tolerance, the block size that we don't use here, and the input table, which is the diff table that we created from the PC diff operation. And then again, this SRID, as I explained earlier, and a feature size. So the feature size indicates the radius of the ball for the pivoting ball algorithm, and this is the algorithm that's used to create the mesh. So essentially it does so by dropping a ball into the point cloud, and when this ball intersects 3 points without intersecting another point, that forms a triangle. And so if it's the ball radius is too small, there's no mesh, and if it's too big, then there's not enough detail. So this can be explicitly provided, and we're also providing the ability to automatically have this calculated by the system. Max angle avoids superfluous mesh if an angle exceeds the value, and if it does, then the mesh stops being created. So for example, if you have an object such as a carpet and the mesh is being created across the top of the carpet and starts to wrap around to the bottom of the carpet, then you have a superfluous mesh as you're feeding across the bottom of it. And so this max angle of 120 in this case would be exceeded, and it would prevent that from happening. And then how many points to read and handle in a single batch, that's just an optimization measure. Finally, we have the operation to clip the tin into an object file. This is creating our CLOB object from that tin. And again, we're taking in the objects from above. Here we can make some additional STO queries, such as a bounding box, where we can bound the mesh by a rectangle, or it can be more complicated. For example, we can bound it by, anything within the state of Louisiana. There is also the where clause, where we can query and filter by something other than spatial. So it's very interesting. For example, the block size, or even business logic. And then these result tables are used during the calculation, but they can also be analyzed unto themselves. The levels of detail argument here only matters if there is different levels of detail. So this is generally used often in visualization tools. For example, when zooming, the level of detail can be changed so that the GPU is not otherwise overwhelmed if you're zooming in or zooming out and there's tremendous detail. And then finally, we have this argument for the block number. So you can filter by the block. So if we're only interested in a particular block. Now we have our CLOB object of the delta between the 2 point clouds that we fed in, and it's in this OBJ file format. So we can finalize this workflow by then writing it out to file and starting and ending with the same use case. We read in the OBJ files from object storage. We could do the same thing from the database. We could write out this delta OBJ file that we've created from the point cloud diff operations to object store or any number of locations. But here's an example of the put object operation where we could go ahead and take the mesh object and put it into object storage. So here we see a simple but very powerful example of the versatility and possibilities that are opened up by the new spatial features in the Oracle Database 23C. Okay, so now we've seen how we can take a simple use case using some complex modern 3D data, put it into the Oracle database, and process it in a number of ways, and analyze it in a number of ways using various different features of the Oracle Converged database, JSON SQL, AIML, and spatial and graph. So I hope you enjoyed that, and thank you very much.